Our last section in this chapter, section 2.6, constructing functions with variation. There are three types of variation we're going to talk about, and really just two types, and then the last one kind of joins them together. So the first type of variation is called direct variation. So direct variation has some different ways it could be expressed. You could hear phrases like y varies directly as x, or y is directly proportional to x. Obviously the key word in both of those is the word directly. And if you have direct variation, what you do is you have an equation that looks like this: y equals kx, and the k value is not 0. Now, I skipped a line, I realize that's actually defining what the k value is. K has a name, it's called the constant of variation, or the proportionality constant. It's a non-zero real number, and it establishes the relationship between these. For example, if I eat 5 apples and each apple has 50 calories in it, then I've eaten 5 times 50 calories. So there's a constant of proportionality in it. It's the number of apples, or number of calories per apple. So that would be an example of direct variation. The other type of variation, truly the second type, is called inverse variation. So for it to be inverse variation, you'll hear phrases like y varies inversely as x, or y is inversely proportional to x. So again, the key word is inversely on this one. And instead of it looking like a equation y equals kx, we get y equals k divided by x. And you might think, okay, yeah, division, it's the inverse of multiplication, and that would be the right kind of thinking. Again, k is called the constant of proportionality, or the constant of variation, the proportional constant, and the k value cannot be 0. Again, it's a real number, it's not equal to 0. And then if we join some of these ideas together, we get something called joint variation. Joint variation has to do with a variable being affected by 2 or more variables. So you'll see phrases like y varies jointly as x and z, or y is jointly proportional to x and z. And again, the joint means that the way that y is connected to x is the same way that it's connected to z. So for instance, on this one, you see direct variation, right? Because there's no division by the variable. So it's y equals x, and then k, and then x z. And again, k is the constant of variation, and it's non-zero. All right, so let's get some examples so you can see how these actually work. To start with, we're just going to construct some functions given some language. So it says the amount of sales tax is directly proportional to the purchase price. And of course, you know this to be true. You go check out at the register, the amount that you actually have for the purchases is going to directly affect the exact amount of your sales tax on your prices, on your purchases, I meant to say. So we're going to create a function that does this, and typically speaking, we'll just use letters that actually represent sort of what the variables are in the problem in terms of the words. So it says the amount of sales tax. So maybe you use S equals, or you use T equals for tax. I'm going to use T. So this is T equals. You always are going to have K for the constant of variation. And then it says it's directly proportional to, so this is going to be K is going to be multiplied by the variable as opposed to being divided. And it says the purchase price, and since it's purchase price, I'll use P. So this is T equals KP. The second one is it says the volume of grain in a silo that a silo can hold varies jointly with the height and the square of the radius. All right, so first of all, again, it was the volume that's doing this, so we're going to use V for volume. It varies jointly, okay, so the constant of variation, K. And it varies jointly would mean that it's going to be 2 direct variations. Jointly with the height is H, and the square of the radius. And the radius would be R squared. Be really careful that you're looking carefully whether it says square or square root, because sometimes people get those backwards just because they're looking too quickly. So our volume will equal KHR squared. All right, now we're going to go the other direction. We're going to write the formula in words using vocabulary variation. Now, if you don't know what these formulas represent, you certainly don't have to use what the letters are. You can just talk about them as being the letters. So you could say something like this. C varies. And how does it vary? Well, it's a direct variation. So you can say varies directly, or you say, here's your language over here, varies directly, or you can say is directly proportional to. Okay, so those are your two options. I already started writing the first one, so I'm going to do the first one on this one. Varies directly. So we could say C varies directly as D. Now, you'll notice that I'm not doing anything about the pi, and the reason I'm not is because pi is a number. Okay, it's not a variable. Pi is a number, and it is actually that proportionality constant that we keep looking at. It's the k value in this particular case. So we're not writing anything about that down. This is just C varies directly as D. Now, on this one, we have y squared on top, and we have the square root of x on bottom. So even though there are two variables on the right, they're not varying in the same way. One is a direct variation because it's in the numerator. The other is an inverse variation because it's in the denominator. So we can't use the word jointly on this one. So we'll say B is, and we'll use the other phrasing of varies directly. So we'll say B is directly proportional to and it's y squared, right? So to the square of y. And inversely proportional to the square root of x. And then we'd be done. Again, the 2 is a number. The 2 is coming about, in fact, it's like 1 over 2. It's coming about as 1/2, okay? So 1/2 is our proportionality constant here. All right, we can actually find that proportionality constant if we're given a little bit more information. So these are examples where we are given a little bit more information and asked to actually find them. So it says to find the constant of variation and construct the function that is expressed in each statement. So we start out by using the language and constructing sort of a partial function with the k value in it. It says h is directly proportional to z. So directly proportional means that it equals kz. Okay, so that's what we did on the previous example, actually example number 1. We just changed that into an equation. However, they give us extra information here about numerical values about our variables. And h is equal to 210 when z is equal to 100. So we can actually plug those in. H is 210 when z is 100. And plug those in for h and for z. And we can find out then what k is. So if we divide this by 100, we find out that the k value, the constant of proportionality, is actually equal to 2.1. Now, it's only half of a question it asks, though. It says to find the constant of variation. We did that. And then it says, and construct the function that is expressed. So we almost constructed the function expressed right back here, right? But it had a k value in it. And we had just said k. We actually know what k is now, so we'll actually find this k, or write our function with this k value in. So h is equal to 2.1 z. So there are two pieces of information that are our answer here, the constant of variation, and then the constant of variation plugged into the function that we started by working with. All right, same directions. P varies directly as the cube root of w. So direct variation, P equals K times, and it says the cube root of W. So the cube root of W would look like this. And then they give us values. P is equal to 6 when W is equal to 8. So K times the cube root of 8. Well, the cube root of 8 is just 2. So my constant of proportionality, I'll divide by 2. My constant of variation, I don't know why I keep saying that wrong. Constant of variation is k equals 3. So one of the answers to the question is k equals 3. The other answer is to plug that k equals 3 back into the function that I created. So p equals 3 cube root of w. Now our last two examples are going to go like one step further. Basically it's going to do exactly what we did on this problem number 3, but then we're going to take that equation that we found, I guess I could box this one in, take that equation that we found at the very end, and we're going to use it to find another value for h or for p, basically if we were using these functions, given the information about z and or w. So let's take a look at an example. Starts out much like the same as before. It says if y is inversely proportional to z. So the first thing to do is to create a statement in a mathematics, an equation, that actually matches that description. It says y is inversely proportional. So inverse means the value of the variable goes on bottom. So the constant of proportionality k can go on top, and inversely proportional to z means z goes on bottom. All right, so that's the starting part. The second piece actually allows me to figure out what k is. When, or if, when z equals the square root of 75, y is equal to 6. So we're going to plug in y equal to 6, and z is equal to the square root of 75, which is a little odd that they gave it to you that way. We are going to simplify that at some point here, what the square root of 75 is. But for now, let's just get k alone, which means multiplying both sides by square root of 75. So my k value is 6 square roots of 75. That isn't simplified. Like I said, it's a little odd that they gave it to you that way. But if you'll remember, 75 is 25 times 3. So this would be 5. Square root of 25 is 5 times 3. So 6 times 5 square root of 3. Or 30 square roots of 3. So that's my constant of variation for k. So this function is actually the same as y equals 30 square root of 3 over z. Okay, so that's basically what we would have done in the last two problems. The last piece of information is the new part. It says what is y when z equals square root of 12. So we can go back in and we can actually plug that in. Y equals, and it's 30 square root of 3 over, and z is the square root of 12. Now don't get carried away. Simplify the square root of 12 before you do anything else, because some pretty nice things happen when you do. 12 is 4 times 3, and the square root of 4 is 2. So this is 2 square roots of 3. You see the beautifulness, right? Those square root of 3's cancel, and then 30 divided by 2 would be 15. So the answer to the actual question is y equals 15. But as you see, there were several sort of stopping steps along the way, that, stepping stones or whatever, that we had to get to. First, we had to figure out what the function's general form is. Then we had to figure out what the constant is, the k value. And then we had to use that equation to actually find y. All right, our last example for this section. If y is directly proportional to the square root of u and inversely proportional to the square of v. All right, so we're going to just pause right there, not even going to read anymore. This right here tells me how I can set up my my variation equation. It says y is directly proportional to the square root of u. So directly proportional means my constant k is multiplied by what they're describing, the square of u. So the square of u would be u squared. Oh, I'm sorry, it said square root. I totally read that wrong. The square root of u, square root u, like this. There we go. And then it says it's inversely proportional. Oh, that's why I got on the wrong line. Inversely proportional to the square of v. Well, inversely proportional means we're going to divide by that part. So inversely proportional to the square of v would be to v squared in the denominator. Okay, so we've created the basic equation. Step 2 is to use the second piece of information where it tells us one of these values to solve for k. It says y equals 7 when u equals 9 and v equals 6. So we're just going to simplify some of these things. The square root of 9 is 3, so this is 3k in the numerator. 6 squared is 36, so that's 36 in the denominator. And of course the 3 and the 6, they reduce to a 12. So I have 7 equals k over 12. We'll multiply by 12 to solve for k. And the k value is 84. So our function with the k value plugged in then is y equals 84 square root u over v squared. All right, and then our last step wants us to find out what is y when u equals 4 and v equals 8. So what is y when u equal 4, so that's square root of 4, and v equal to 8? That's 8 squared. All right. Well, square root of 4 is 2, so I have 84 times 2. That's 168. And then, of course, 8 squared is 64. I can either divide these and write them as a decimal because it does end up being terminating, or I could write them as a simplified fraction. If I simplify the fraction, I get 21 over 8. If I simplify it as a decimal, I get 2.625. And either of those would be perfectly acceptable answers.